This is a continuation of our Lecture 3 on set operations. Last time what we did is we concluded with this proof that the complement of the intersection of A and B is equal to the union of the complements of A and B. We did this by showing that the complement of the intersection was a subset of the union of the complements. And following that up, we showed that the union of the complements was a subset of the complement of the intersection. So this is an example of how we have to prove equality with sets. One, the left-hand side has to be a subset of the right-hand side, and vice versa. The right-hand side has to be a subset of the left-hand side. We now continue with example 11. Use set-Miller notation and logical equivalences to establish that the complement of the intersection is equal to the union of the complements. Solution: to show that the complement of the intersection is equal to the union of the complements, we will show in the same way that first that the intersection of the complements is equal to the union of the complement of A and the complement of B, and then the reverse, that the union of the complements is equal to a subset of the complement of the intersection. And you can see here that what we have done is we have used our propositional logic and our definitions. We begin with step 1, that X is an element of the complement of the intersection, and we proceed through definitions and De Morgan's laws for propositions to come to our conclusions. I like this method of doing a proof. It's not written on a paragraph. It's done step by step. Each time we make a transformation, we give a justification, which is something that we've already proved, or a definition that's given in the book prior to this discussion. In a similar way, what we can do is we can show that the union of the complements is a subset of the complement of the intersection. And we use the same technique for this, going step by step through the proof. Finally, here is an example using a technique that we had done with propositions to build supporting expressions. Use a membership table to show that A intersect the quantity B union C is equal to the quantity A intersect B union the quantity A intersect C. Solution: the membership table for these combinations of sets is shown below in table 2. The table has 8 rows excluding the title row. Because the columns for A intersect the quantity B union C and the quantity A intersect B union the quantity A intersect B are the same, the identity is valid. And we can see how we constructed this. Example 14. Let A, B, and C be sets. Show that the complement of A union the quantity B intersection C is equal to the quantity that is the union of the complements of B and C with the intersection of the complement of A. So we take our original expression and we apply the first De Morgan's law, and so our unions are changed to our union with the quantity is changed to an intersection, and we complement both halves. Then what we do is we proceed to complement. You apply De Morgan's law to the intersection, and we arrive at the union, and then we commute things to make them look like our desired product. Generalized unions and intersections. Example 15.1. Let A be 02468, B equal 01234, and C equal 0369. What is the union of A, B, and C? Solution. The union of the sets A union B union C contains those elements, at least one of A, B, or C. So we can see that the union is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 15.2, A, B, and C are as in example 15.1. And what is the intersection of A and B and C? And it contains those elements that are common to all three. And so there is one element only, and that is 0. Computer representations of sets. Assume that the universal set is finite and of a reasonable size so that the number of elements of the universal set is not larger than the memory size of the computer being used. First, specify an arbitrary ordering of the elements of the universal set. For example, A1, A2 through AN. Represent a subset A of the universal set with a bit string of length n, where the ith bit in the string is a 1 if A sub I belongs to A, or 0 if it does not belong to A. Example 18.1. Let U be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the ordering of the elements of U has the elements increasing order, that is, A sub I equal I. What bit string represents the subset of all odd integers in U? The bit string that represents the set of odd integers in U, namely 1, 3, 5, 7, and 9, has one bit in the first, third, fifth, seventh, and ninth positions and a 0 elsewhere. It is 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Let U be the universal set be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the ordering of elements in U as the elements in increasing order, that is, A sub I is equal to I. What bit string represents the subset of all even integers? And it is the complement of the odd integers, as we can see 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Let U be, as before, what bit string represents the subset of all integers that do not exceed 5 in the union? The solution is the bit string is the set of even integers in U, namely 1, 2, 3, 4, 5, has one bit in the first 5 positions and a 0 elsewhere. It is 1, 1, triple 1, 0, quadruple 0. Using bit strings to represent sets, it is easy to find the complements of sets and unions, intersections, and differences of sets. Define the bit string for the complement of a set. From the bit string for that set, we simply change each 1 to a 0 and each 0 to a 1. We complement the bits in the string because X is an element of A if and only if X is not an element of the complement of A. Note that this operation corresponds to take the negation of each bit when we associate the bit with a truth value, with 1 representing true and 0 representing false. Example 19. Let U be the universal set be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the ordering of the elements in U has the elements in increasing order. What is the complement of the set 1, 3, 5, 7, and 9? The complement of each bit in the set, the original is 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. Hence, the complement is 0, 1, 0, 1, 0, 1, 0, 1. The complement corresponds to the set 2, 4, 6, 8, 10, the even integers of U. Now we have some example exercises. Let A be the set of students who live within 1 mile of school, and let B be the set of students who walk to classes. Describe the students in each of these sets. Well, the intersection of A and B is the set of students who live within 1 mile of school and walk to class. The union is the set of students who either live within 1 mile of school or walk to class, or both. The difference, A minus B, is the set of students who live within 1 mile of school but do not walk to class. And the reverse difference, B minus A, is the set of students who live more than 1 mile of school but nevertheless walk to class. Exercise 3, let A be 1, 2, 3, 4, 5 and B 0, 3, 6. Find the union of A and B. The union of A is 0, 1, 2, 3, 4, 5, 6. The intersection is 3. The difference, A minus B, is 1, 2, 3, 1, 2, 4, 5, and B minus A is 0 and 6. Prove the domination laws in Table 1 by showing that the union of A and the universal set is the universal set. So you can see I'm using the representation that I prefer, which is that we have a step-by-step process. So we start with A union B, start from the left-hand side. The goal is to transform the left-hand side transform the left-hand side to the right-hand side. We apply the definition and turn this into a set formation so that we can apply the laws that we've already established for proposition. If we have A union the universal set, what that means is the set X, where X is an element of A, or X is an element of the universal set. The universal set contains all elements, and in particular X is an element deal, so we transform X as an element of deal to true, since all X are an element of the universal set. The OR operation with any proposition we've established is always true. So we have the domination labels for propositions and we arrive at the universal set. We use the same kind of technique to show that the intersection of A with the empty set is the empty set. We start with the intersection of A with the empty set. We change this to set representation. That is X, the set X, where X is an element of A and X is an element of the empty set. Since no element is an empty of the empty set, we can change that to false. And we can use the domination laws for propositions to find that X, where false, coming up with the empty set here at the end. Let A and B be sets. Prove the commutative laws from Table 1 by showing that A union B is equal to B union A, and A intersection B is equal to B intersection A. And we use this set representation again. We start from the left-hand side, A union B, and we come up with a set representation, X, where X is an element of A, or X is an element of B, and we can reverse these by the proposition laws coming up with the definition of a union. We use a similar technique for the intersection commutativity laws, and that concludes our lecture.